Hello, and welcome to our technical training on Thunder DNS. I'm Ryan Rowley, co-founder and general manager. I've also got Rob from our technical team who will join us. Over the next few minutes, we will provide an overview of Thunder DNS. Specifically, we will review the solution architecture, features, and implementation guidelines. We'll finish our discussion by walking through our graphical user interface and demoing a few of our product features. Before getting into the technical details, I want to make sure everyone understands the objective of Thunder DNS. This understanding should be helpful during our technical discussion, as we've made several optimizations to tailor Thunder DNS for our specific goals. The objective of Thunder DNS is to protect the next billion new users, organizations, and devices from cybersecurity threats. This group generally lacks the expertise, experience, and financial means to protect themselves, so we've built Thunder DNS to provide an affordable cybersecurity solution.
All right, let's get into the high-level architecture of Thunder DNS. To start, we'll provide a quick refresher on the different networking and security layers. Next, we'll provide a detailed description of how DNS is able to look up the IP address of any domain. And then we'll show the architecture of Thunder DNS and compare it to the architecture of a typical recursive DNS server.
Here is a graphic that illustrates how users connect and how multi-layered security is implemented. At the core is the users. This is because all communications are designed to help someone do something. Devices either provide a way for the user to communicate with the internet directly, like we do on our computers, or the devices can connect directly to the internet in behalf of the user, which is common in IoT applications. The network allows the devices and users to communicate with each other, and the internet allows multiple networks to connect to each other. Best practices in cybersecurity is to implement layered security, which is having elements of security at each layer. For example, for the user layer, you could implement training to help users identify security threats. At the device level, you can implement antivirus as endpoint protection. Firewalls, IDS, IPS, UTMs all focus on network level security. And our Thunder DNS product is at that internet layer. It focuses on providing the first layer of protection against security threats. We decided to start protecting the next billion with a DNS-based security solution because it's universal, it's scalable, and it's low cost. When it comes to the internet, the domain name system, or DNS, is the equivalent of the modern-day Yellow Pages. DNS does a lookup for any domain and provides the corresponding IP address so a device can start up a connection. This process is actually more difficult than it sounds because a domain website may be hosted by different servers depending on the location, and the content of any domain could be served from different servers and reconstructed by the web browser. These technical nuances make keeping a static list of DNS lookups impossible. DNS has to be a dynamic distributed system. Let's walk through how an unknown DNS query is resolved. To start, a user or device wants to access a specific domain and sends the request to a DNS resolver, which we call the DNS server or recursive DNS server. DNS queries used for IP lookups are called recursive queries, which means the response can either be the IP address or an error. The recursive DNS server holds a cache of common DNS queries. In this case, let's assume that the domain is not common, so the recursive server needs to go find the IP address. The DNS server sends an iterative query to the nearest root DNS server cluster to figure out where the domain is located. The root clusters manage all internet assigned numbers, and the management of the root servers is done by a few organizations such as VeriSign that report to the Internet Assigned Numbers Authority, basically the guys that manage all of the IP addresses for everything. The root server will not know the IP address of the domain or the authoritative name server, but it sends a response to the DNS server with the correct top-level domain, or TLD servers, that have this information. The DNS server then sends an iterative query to the TLD servers. The TLD servers manage specific top-level domains such as .com, .org, or .io. They may not know the IP address of the requested domain, but they will know the authoritative name server that has that information. In that case, the DNS server sends a query to the name servers to look up the IP address of the requested domain. The authoritative name server is responsible for resolving the domain query and provides the DNS server with the domain's IP address. The DNS server then passes that information back to the device, and the device reaches out to the domain's IP address to establish a connection.
Below is a simplified graphic of the domain name system. Basically, recursive queries are sent from the device to the DNS server, and the server provides a response of an IP address or a failure error. The failure error is the key to transforming DNS from a simple IP lookup tool into a powerful security solution. If the DNS provides a failure error instead of an IP address, then the user and the device is not able to communicate with the IP address. No IP session takes place because the device never reaches out to the server in the first place. We leverage this native DNS error protocol to protect the next billion from malware, ransomware, and phishing. 91% of these types of attacks use DNS to contact their host domain. By blocking those DNS queries, the devices and the users are protected without even knowing a potential threat existed. The challenge for us then is building an evolving solution that can keep up with the threats and identifying which queries to block.
Here is a graphic that provides an overview of Thunder DNS's architecture. The main orange line represents the inline path of the recursive query lookup request. The gray lines represent work that is being done outside the query's path. We will go through each component of our solution in detail, but to provide you some context, you can see the domain name system at the bottom right-hand corner. Thunder DNS is not designed to be a better DNS server. Instead, we built a security system that integrates DNS technology. Let's start by reviewing the inline components of our solution. On the far left-hand side, you can see the query entering the slide. This represents the query lookup request coming from a device. Remote tunneling allows for devices behind a private NAT on external networks to use Thunder DNS as well. Once the queries hit Thunder DNS, they must pass through our DNS cloud firewall. When the queries come into Thunder DNS, the firewall blocks by domain. And when the query response is returning to the device, the firewall blocks by IP address. After the firewall, the queries must pass through our content filter. The content filter can block domains based on category, maturity rating, and country IP address. After the content filter, our decision engine determines the risk level of the query and decides to either have it inspected on our DNS cloud backend or resolved through a standard domain name system. The DNS query is resolved, and then the query and response are passed back to the requesting device, assuming it makes it pass our filter and firewall again. From an end user perspective, they will not see any noticeable impact to their traffic unless Thunder DNS decides to perform real-time inspection. In that case, up to a few hundred milliseconds will be added to those queries. Thunder DNS is also performing other work designed to protect users in the background. Thunder DNS extracts metadata out of each query. That information is stored locally for network analytics and reporting. Subcomponents of the metadata are anonymized and sent to our anomaly detection feature. We crunch that information using big data and artificial intelligence heuristics to find patterns in the data and identify unknown threats. Results from our anomaly detection and external threat signatures from other sources are compiled and sent to update the cloud firewall, content filter, and decision engine.
Let's spend a few minutes reviewing the features of Thunder DNS. Feel free to watch our company overview or other videos for a detailed explanation of each feature. The focus of our discussion will be primarily on the technical implementation requirements and limitations of each feature.
Thunder DNS has built-in tunneling features that allow devices connected to external networks to securely send their DNS queries to Thunder DNS. We can even do this for devices with a private IP address behind a NAT by using the Layer 2 tunnel protocol, also known as L2TP, inside an IPsec tunnel. This tunnel architecture provides three major advantages over existing solutions on the market. 1. L2TP and IPsec are standards-based solutions and should work on most all client devices without having to install a separate utility. 2. IPsec protects against any tampering of the packet markings when in transit. And 3. IPsec tunnels usually can be established without creating additional holes in your existing firewall. You can set up custom filtering settings on each device that has an assigned L2TP tunnel. This allows for granular content control down to the specific device. Within L2TP, we allow for up to 64 unique DSCP markings per device, and there is no limit to the number of custom templates that can be created. This is very helpful in home or office scenarios where you want different profiles on the same network. For example, you could create an L2TP tunnel with a router and then set up to 64 unique profiles for different user applications. Thunder DNS does not limit the number of devices or L2TP tunnels that can be set up. However, the server will be limited by the hardware CPU. A good rule of thumb is each server should be able to support around 1,000 unique devices or tunnels. If additional tunnels are required, then you can either increase the server's hardware resources or load balance by adding another server.
The DNS Cloud Firewall protects against malware, phishing, ransomware, and other threats trying to access the open internet. The firewall blocks domains that are known to be threats, as well as known IP threats, before the device gets the resolved DNS query. Thunder DNS's firewall works at two levels, a system level and a server level. The system level provides a list of known threat signatures that are pushed to all Thunder DNS servers. This list is compiled from our anomaly detection and from several external signature sources. We update the system level signatures several times each week. The server level DNS firewall allows custom firewall configurations that can be defined specifically for each server. This includes blacklisting or whitelisting specific domains or IPs. Thunder DNS allows up to 10,000 unique server-level firewall configurations. Thunder DNS's content filter was designed to protect the next billion from having to view unwanted content. We do this by dropping DNS queries from domains that do not meet our specific criteria. We categorize many popular domains by category and intended audience. We store that information locally in a database on each server. New domains are categorized within few hours, and category updates are sent automatically to all Thunder DNS servers. We offer around 50 different categories as well as 4 different intended audience content filters. We can also filter out international communications for specific countries by IP address to provide another layer of security.
Our DNS decision engine is an internally developed algorithm that determines the risk level of every DNS query. It tries to determine if it's worth spending a few extra milliseconds to inspect a DNS query prior to resolution, or if it's safe enough to go through standard DNS resolution. The goal of Decision Engine is to identify the most risky and uncommon queries so that Thunder DNS can perform additional checks prior to the DNS query being resolved. The challenge is the additional security checks require the query to be processed in the cloud, and the result is a few added milliseconds of latency. Because of this, we only want to inspect the most risky traffic real time. Our target is less than 1% of all DNS queries. The determination is based on the popularity of the domain, how often it is queried, the requester IP address, and several other factors. Thunder DNS records the result of every DNS query and provides the information to the users in two ways. The first is in real time on our system dashboard. In the dashboard, we provide information about each user, domain, and category of each domain on the network. You can see which domains or IPs were blocked and how many times Thunder DNS blocked them. Most query information updates every few seconds. However, some of the information is only processed every few minutes to save on CPU. The cybersecurity industry has already proven that DNS data is effective in identifying unknown security anomalies and threats. Some of the common DNS heuristic techniques in the industry are tracking changes in the number of queries and responses, monitoring the number of MX queries, and tracking the number of error responses. For tracking changes in the number of queries and responses, large changes generally indicate a configuration change or active threat. For monitoring the number of MX queries, a spike of MX queries may indicate a host being used for spam. For tracking the number of error responses, a spike of errors may indicate command and control malware trying to locate its mothership. Thunder DNS integrates multiple heuristic models, and we combine the output of these models to increase the accuracy of our anomaly detection feature. We also have access to a huge relevant data set of 300 million new queries from 180 countries each day. We use this large data set to provide context for individual queries to identify anomalies and unknown threats.
Once identified, the new threat signatures are sent to the cloud. We combine threat signatures from anomaly detection with other threat signatures we've obtained from external sources. Thunder DNS pushes updates to each server automatically. Auto updates ensures that each server has the latest threat signature definitions, as well as provides category updates on new domains.
Let's move on to discussing typical deployment scenarios and do a walkthrough of our user interface. As a reminder, Thunder DNS is a virtual image, not a physical hardware box. This allows Thunder DNS to be flexible and work for several different deployment scenarios. Most service providers we work with are either reusing their old physical DNS servers, loading our image as a virtual machine on an ESX host, or loading our image on a cloud server, such as AWS, Azure, or Google Cloud. Any of those scenarios will work well for Thunder DNS, and although the installation process will vary, the general server setup will be the same for all deployment types. Typically, Thunder DNS is hosted at the data center, which offers access to low-cost, high-uptime bandwidth. This is also convenient to allow Thunder DNS to be used for on-network and out-of-network devices. With a few routing rules, you can set all devices on the network to use Thunder DNS as its DNS server. And for out-of-network devices, you can set up separate tunnels to virtually route all DNS traffic to Thunder DNS. Once deployed, configuration changes can be centrally managed instead of having to update each client device. The physical hardware resource requirements will vary depending on the number of devices, users, and tunnels that will use the server. Our general recommendation is at least a 1.5 GHz dual-core processor with 4 GB of RAM and 10 GB of hard disk space. Since Thunder DNS also performs critical DNS lookup functions, we recommend installing at least 2 server instances on separate physical hardware to provide redundancy.
All right, let's quickly walk through the Graphic User Interface, or GUI. Once Thunder DNS is loaded on a server, a user needs to create a local account. After the account is verified, the user logs into their account and hits the main status page. The top three boxes show counters on the number of DNS queries processed, inspected, and blocked. The user can click on the blocked queries to learn which queries were blocked as threats or filtered content. The main graph on the status page shows detailed information about all the DNS queries as well as server performance. The user can select the drop-down to see specific traffic information and view performance over time. The System Information table provides a quick reference guide of information on Thunder DNS. Also, you will see white icons throughout our UI. These provide detailed descriptions of each element on the page.
The DNS page is the core command center of Thunder DNS. To start, each server needs to be set up with the subnets that Thunder DNS will allow. Users can allow all subnets by adding the rule 0.0.0.0/0 or specify the subnets they want to allow. Once set up, Thunder DNS will be available to provide DNS services for the allowed subnets. After that, a user can enable or disable features, whitelist or blacklist specific domains or IPs, configure specific firewall rules, or set up content filtering. Changes to the DNS are applied immediately, and Thunder DNS will begin blocking DNS queries that do not meet the setup criteria. With that said, it may take a few minutes for the change to propagate to the devices, since most devices cache DNS queries based on the TTL of the domain. Also, changes in the DNS page will impact all devices using Thunder DNS, so be careful. Use L2TP tunnels and DSCP markings to apply specific rules to a limited number of devices. L2TP remote tunneling is used for two main purposes. One is to create a tunnel to use Thunder DNS using any ISP, or when the device is behind a private NAT. Or two is to create custom content filters and apply them to specific network devices. Often, customers will use the L2TP tunnels for both issues. We always recommend using L2TP with IPsec to prevent changes to the DSCP markings, as well as lowering the chances of upstream firewall issues. However, L2TP without IPsec is also supported. To configure the server for L2TP connections, Thunder DNS requires the user to provide an IP address pool that will handle those connections. The L2TP mappings table shows L2TP status and maps the devices to templates and DSCP markings. DSCP markings are important as they allow for up to 64 different profiles for a single L2TP connection. The default DSCP marking of 0 should be used if only one filter is going to be applied to the device or LTP tunnel. The device table is used to set up new devices and allow for unique username-password combinations per device. And the template table is used to create filter templates that can be applied to any device.
The server page shows basic server settings and allows the user to perform server and support tasks. The network page allows for manual configuration of the server's IP's settings. By default, the server looks for a DHCP to get an IP address. However, once logged in, the user can manually set the IP address to a static address. Lastly, the account page provides information that is associated with the active server license key. Each server needs a license key to be activated, and that license key is checked periodically to ensure the server is up to date.
Now that we've reviewed Thunder DNS's architecture, features, and user interface, let's spend a few minutes doing a demo to show how it works. The nice part about this demo is that you can follow along on your device to see Thunder DNS in action as well. To start, let's do something simple. Let's open up a web browser and go to thunderdns.io. You should be able to get to thunderdns.io on your computer without any issues. Now, let's pretend that Thunder DNS is a security threat. Since we are pretending, we will have to block the thunderdns.io manually, but if it was a real threat, our system would block it automatically. To manually block the domain, we will log into the Thunder DNS server and blacklist thunderdns.io. Now that the rule is applied, I can open a new browser and see that we can no longer get to thunderdns.io. You can also see this work on your device by setting 104.225.250.61 as your DNS server. I'm using a MacBook, and I can change the settings by opening my network settings and clicking on the DNS settings in the advanced section. Once set up, you will also see that thunderdns.io is blocked on this server. After, I recommend you change your device settings back to the default DNS, as this is a simple demo server.
So that's all we plan to discuss. Hopefully we provided an overview that helps you understand the technical capabilities of Thunder DNS. We appreciate your interest in Thunder DNS, and please send any feedback or questions to support@thunderdns.io.